If we have two arrays of numbers, there are different ways to combine them, such as dividing, multiplying, adding, or subtracting. However, there is another important operation called convolution. In this video, I will walk you through the step-by-step process of convolution for 1D time series data. I will explain the mathematical formulation, provide practical examples, and demonstrate how convolution can be applied to uncover valuable insights in your data. Let's explore how mathematically convolution is defined. Convolution between two functions here, xt and ht, is a mathematical operation that combines the information from both functions to produce a new function, which is shown by this formula. One function here, xt, represents the input time series, and the other function represents a kernel or filter. The kernel is usually a smaller window of data that slides or shifts along the input time series. Mathematically, convolution involves taking the integral of the product of these two functions. If you consider the time series xt using different kernels or filters, enables us to extract useful information, say identify patterns, remove noise, smoothing or highlight specific features within the data. In short, one signal can be used with different kernels. For example, to smooth a time series, we use typically a low-pass filter, such as Gaussian kernel, or a moving average kernel and exponential smoothing kernels. These kernels are designed to attenuate high-frequency components in the time series, resulting in a smoother representation of the data. I will translate this formulation graphically to better understand the concept. Assume we have input time series xt. To perform the convolution operation, we first need to transform our variable from t to tau. Through a change of variable. The next step is to determine the kernel or filter, as it defines the type of operation we want to apply to the input signal. After determining kernel, we flip or reverse its order. In the context of the convolution formulation, the variable t minus tau indicates that for a given t, tau varies over the entire computational interval. Therefore, we need to reverse the order of the kernel and then shift it by t before performing the convolution operation. To perform the convolution, we slide the kernel along the time series. At each time t, we multiply the corresponding values of the kernel and time series and sum the results. Now I will provide a visual explanation of the convolution using two functions as an example. I convolve a triangular waveform xt and a pulse function or rectangular function ht. The resulting function represents the overlap or combination of the two original functions. The first important step in calculating the convolution integral for a time series is to prepare the function involved. As mentioned in the previous slide, we will be integrating with respect to the variable tau. While the change of variable for the time series x does not affect the calculation, we need to manipulate the kernel function h. to account for its independent variable being t minus tau. To obtain h t minus tau, we first flip the kernel h tau with respect to the vertical axis. This flipping is represented by the red dashed lines in this figure. After flipping, we then shift h minus tau by t to get h t minus tau. For the purpose of demonstration and simplicity, let's assume that t is between 0 and 1. The resulting shifted kernel h t minus tau is shown in this figure. Now let's consider different cases by varying the value of t from negative infinity to positive infinity. In the first case, for all t less equal 0, there is no overlap between the input time series x tau and the kernel function h t minus tau. As a result, the convolution in this case is 0. In the second case, for values of t between 0 and 1, there is an overlap between x tau and the kernel function within interval 0 and t. In this interval, the function x tau is equal to tau. As shown in this figure. And the kernel function h t minus tau is equal to 1. Therefore, the convolution is simply calculated by integrating tau from 0 to 1. In the third case, for all values of t between 1 and 2, there are overlaps between the input time series x tau and the kernel function h t minus tau in the interval t minus 1 and t. In this interval, the kernel function h t minus tau is equal to 1. However, we need to elaborate on the function x tau, which has two different relations depending on its interval. Specifically, x tau is equal to tau for tau values between t minus 1 and t, and it is equal to 2 minus tau for tau values between 1 and t. To calculate the convolution for this scenario, we need to split the integral into two parts. The first integral corresponds to the interval t minus 1 and 1, and x tau is set to tau. The second integral corresponds to the interval 1 and t, and x tau is set to 2 minus tau. By inserting the appropriate integral bounds, you can evaluate these integrals to obtain the value of the convolution for this case. In the fourth case, t varies between 2 and 3. And there is an overlap between x tau and h t minus tau in interval t minus 1 and 2. ht minus tau is equal 1 and x tau is set to 2 minus tau in this interval. The convolution integral is then calculated by this relation. For all values of t greater than 3, there is no overlap between x tau and ht minus tau, and the convolution is then 0. Here you can see the sliding of kernel function and overlapping regions between the original time series indicated by black color and the kernel function shown in red. The convolution is then represented by black markers and blue curve.